So what if I told you the fastest way for your solar system to pay for itself is by using this little stainless steel tube? Well, I've tested this over the past 2 months and I've got the data to prove it. So let me explain and show you what I mean. So to get the most out of our solar system, we need to maximize the use of solar power because it is free, and we need to try and minimize the use of our grid or utility power because that's the power that we need to pay for. And this is especially true for high power devices, things like electric water heaters or geysers as they are known in South Africa. So if we can set these up to use as much power as possible during the day, and if they need to use power at night, then we set them up to use the bare minimum amount of power that we need to heat the water, because generally at night we're using grid or utility power which we need to pay for. And if we can get this all set up correctly, this will all result in a faster payback period for our solar system, and that is where this stainless steel tube comes into play. So to do this, we need some sort of smart control, possibly using an app on our phone that is preferably easy to use, or maybe even some type of system that draws information from our inverter and it uses a solar forecast and a load shedding schedule. If you're not from South Africa, we have rolling blackout, so it uses this rolling blackout schedule, and then it calculates the best possible time to heat our water for the lowest possible cost. And this makes a huge difference if you have large electric water heaters or maybe multiple geysers in your house, because if you don't manage this power usage correctly, it results in quite a large cost. But if you do manage the power usage correctly, it can result in quite a large saving. So why can't we just use a normal timer that heats the water up once a day? Well, here's the thing. These normal timers are not very smart. In fact, they only really monitor time. And there may be various times where you are heating water hotter than it needs to be with power that you're paying for. And of course, this isn't very efficient. So this is the solution that I came up with. So the first step is that we need to be able to accurately monitor the water temperature, and from there set up a couple of rules or conditions about how hot the water needs to get and at what specific times. So for example, on a normal day, the best chance of covering the full load using solar power would be from about 11 a.m. to maybe around 4 p.m. in winter. Now, of course, in summer, this time period will be longer, but we are approaching winter at the moment. So the geyser needs to turn on at 12 o'clock and then heat up to its maximum temperature of 65 degrees Celsius, and then the geyser must turn off again. Also, at any time between 12 o'clock and 4 p.m., if the geyser temperature drops below 55 degrees Celsius, it must turn back on and then bump the temperature back up to 65 degrees C, and then after 4 p.m. it must turn off again. Now this way, entering each evening, we have enough hot water for 2 hot showers at night, and from the testing that I've done over the past 2 months, as the water cools overnight, we still have enough for 2 hot showers in the morning without any additional heating. Then when 12 o'clock rolls around again and the cycle continues, the water is then once again heated with solar power. But what happens if there was more hot water used in the evening than normal? And then this may result in cold water for the morning showers. Well, this is where the second timer and the importance of the accurate temperature monitoring comes in. So between 4 and 5 a.m., if the water temperature is below 35 degrees C, the geyser must turn on and bump the temperature up to 45 degrees Celsius and no higher. So this way we are increasing the temperature enough to have a hot shower, but we're not making it any hotter than it needs to be. Because of course, any hotter and we are just paying to heat the water that won't be used. Now, when 12 o'clock rolls around again, the water can be heated with solar power once again, which of course doesn't cost us anything. Now, we haven't fully entered winter yet, but over the past 2 months, we've only needed to heat our water once per day using solar power. Now, of course, as winter rolls around, the temperatures decrease and the nights get longer, but there is still some improvements that we can make to the system because none of our geysers have got geyser blankets. So maybe I need to do a little bit more testing over the winter period. But to get all of this done, I also had quite a tall order of requirements which I actually think are very important. So first thing in the list is that the geyser or switching device needs to have at least 2 sets of time and temperature based conditions that can be set. Number 2, I don't want to make any modifications to the geysers, and we don't compromise on safety. Number 3, I want to use the existing geyser element and thermostat so that we still have a backup or a secondary mechanical thermal control in case our smart thermal control fails to turn off the element. Number 4, I want to use off-the-shelf parts, but a little bit more about this later. Number 5, I want to use an existing app with no special programming required, so that the average person is quite easily able to use the system. Number 6, I want to be able to accurately monitor the water temperature, so that if we need to use our battery power or grid power to heat the water, we are only heating it as much as what is needed and no more. Now this next one might not apply to everybody, but number 7, because we've got multiple geysers, I would like all of these geysers to be automatically controlled in sequence, but also to have a manual override. And lastly, number 8, to only heat the water when there is excess solar power available. But more about this later on in the video. So as you can see, it is quite a tall order of requirements. So I've chosen to go with the Sonoff THR320 smart switch and with the WTS01 waterproof temperature sensor, and of course the stainless steel tube adapter. Now according to the specs, it can handle 20 amps, so it's a perfect fit for a 2 kilowatt geyser element, which is about 9 to 10 amps, or a 3 kilowatt element, which is about 14 or 15 amps. And we may be skirting the limit of a 4 kilowatt geyser element, which is about 18 or 19 amps. So in order to meet these requirements and accurately monitor water temperature, I need the temperature probe to pick up the water temperature deep inside the geyser. And this is what I came up with. So I'm just going to quickly weld up a stainless steel tube adapter that can screw into one of the existing ports on the geyser. Now I want to use these existing ports so that we don't have to modify the geyser in any way, and this way we keep everything as safe as possible. And I also don't want to touch any of the existing pipework, and I'll show you how it's going to be installed shortly. So this tube will stick into the water, and the temperature probe will be able to slide into the tube and pick up the water temperature pretty accurately. Now I realized I said one of the requirements was to use off-the-shelf parts, but here I am welding up a custom part. So what is up? Well, I'm actually considering selling these little stainless steel adapter tubes. So depending on how much demand there is or what inquiries I receive, let's see how things go. Now, if you are interested in something like this, leave us a comment. I might also include this in an online store. So if I do, I will leave a link to that in the description. So maybe go and check that out. So this is a Sonoff temperature probe, and you can see that it slides into the tube without any problems. So once the tube is installed, the probe can be inserted and removed very easily. Now the probe does fit into the tube fairly well, but there is a small gap and I'd like to try and close that gap up. So I ended up cutting a short piece of copper pipe, like normal water copper pipe, cutting a section of that pipe out and then rolling it into a smaller diameter. And luckily enough, the copper is fairly soft, so it's easy to work with. So I've rolled it very slightly smaller than the probe so that as I tap it onto the probe, it makes solid contact. Now, if you guys make one of these copper sleeves, it must just be tight enough to make contact with the probe and no more. Almost like you can push it on by hand. So I'm really not tapping it very hard with a hammer. So now you'll see the fit inside the tube is quite a bit tighter, so the heat transfer should be really good. But I also think this would work fairly well without the copper sleeve. So now I need to go ahead and install the tube. So the first step is to turn off the water supply and the electrical supply to the geyser. And once that's done, I need to drain the water to just below the halfway mark. Now I'm going to be installing this tube adapter in place of the anode, and I'll move the anode to the other side of the geyser. Now most geysers should have a hole for 2 anode probes, or sometimes geysers have multiple inlets and outlets, so you should just be able to pick any one of these that suits you best, and they should all be the same size. So I'll go ahead and remove the old anode and then clean out the threads, and clearly we can see that this anode needs to be replaced. So once the threads are clean, I'll test fit the tube to make sure that it easily threads in all the way. Next, I'll apply some PTFE tape or thread tape and then install it properly. Now, one thing to keep in mind is that this fitting has a tapered thread. So it only screws in up to the taper and then it gets tight. Once it's tight, it just needs to be nipped up. Now I'll go ahead and stick the probe in. So I'm not sure if you noticed, but the probe is a piece of protective plastic pipe around the wire. So have a close look here. So this is a piece of old 6mm airline I had lying around. And what I did is cut a slit along the length with a pair of scissors, and then I slid it over the probe's wire to protect it from heat. Now I'm not sure if this is strictly necessary, but I had the tube lying around, so I used it. And now the other end of the probe needs to be plugged into the on-off switch. So the wire on the temperature probe is only about 1 meter long, so the Sonoff TH320 switch needs to be installed pretty close to the geyser. And you'll notice that the Sonoff switch is being installed in one of those external waterproof plug boxes, and that's just been screwed to one of the roof trusses. And the power supply wire first runs through the geyser isolator, then the power comes out of the isolator and then it goes into the Sonoff switch, and then it comes out of the Sonoff switch and then it goes to the heating element in the geyser. And in this case, I was lucky enough that the original wire had enough slack so that the wire could just be cut and the Sonoff switch could be teed in. And here's another close-up of the wiring into the Sonoff switch, with the live and the neutral supply wires feeding in here, and the neutral and the switched live wire feeding out here. And then once everything is connected, the box can be closed up. So this is the other side of the geyser where the new anode will be installed. And here you can see a comparison of the new and the old anode. Now this is being installed into a 150 litre geyser, but if you are installing the temperature tube and a probe into a smaller 100 litre geyser, for example, those geysers are a lot shorter. You may need to cut the new anode shorter by about 120 millimeters. Or if you are using an existing anode, remove that and cut 120 millimeters off of that. Although you do need to be careful because not all geysers are going to be the same. The different makes and models may be different lengths. The point of this is to make sure that once you screw the anode into the one side of the geyser and the temperature tube into the other side of the geyser, that there is a gap between the two. You don't want them pushing up against each other and then you're trying to screw the one against the other, and then you'll probably end up damaging both items. And here's an example of the end of an anode that has been cut off, and I've got 120 millimeters written on it. Now, as I was trying to explain earlier, your mileage may vary. You may have to cut off less or more, or you may not even have to cut off anything. But what I was trying to explain is that when you install the temperature probe from the one side of the geyser and the anode from the other side of the geyser, you don't want these to be pressing up against each other and then you're screwing each one in and they're fighting against each other, and then you'll end up probably damaging and bending your tube or maybe damaging the anode. So I think the best case scenario is going to be to loosely thread both of these in by hand and feel and make sure that they are not hitting each other. You could also maybe screw one in from one side of the geyser and then stick a tape measure in from the other side and measure the distance up to the end of the probe or up to the end of the anode. Either way, just be a little bit careful, but generally this is only a problem with the smaller 100 litre geysers. Anything from 150 litres and larger shouldn't really be a problem, but just make sure that you check it out. And of course, once everything is installed, you can turn on the water and then let the geyser fill up all the way and then check for any leaks. And also don't forget to turn on the power. Then you can go ahead and connect your Sonoff device to your Wi-Fi and then load it to the app, and your Sonoff device should come with instructions on how to do all of this. Now, some geysers might have inlet or outlet ports with a male thread, and in this case we just use this little stainless steel coupler and then we screw it onto the tube, and that leaves us with a female threaded end that can screw onto the male threaded port on a geyser. Now, I have seen a few other methods for installing these temperature probes, and the first one is to use a brass T fitting installed on the hot water outlet. Now, my thoughts on this is that it's not an accurate indication of the average water temperature in the geyser, and it will cool when the water doesn't flow through the fitting, and of course when you open a hot water tap and water starts to flow, then the temperature probe will heat up. The second method I've seen is to drill a hole in the plastic end cap of a geyser and then shove your temperature probe between the insulation and the inner vessel of the geyser. Now this does sort of work because I have tried it, but I found it to be not very accurate, and it's a little bit fiddly to get the probe pressed up well enough against the inner vessel of the geyser for good heat transfer. And the third method is installing a really small temperature probe in the same pipe that the original thermostat goes in, along with the original thermostat. So trying to put them both in that same little hole together. I don't really want to tamper with the standard geyser thermostat because we want to use this as a fail-safe in case our son-off or our smart device fails. Now what I mean by this is that our son-off device is set to turn the geyser element off at 65 degrees C. But what happens if that fails? Well, then we've got our mechanical thermostat, the original one that came with our geyser. We're going to set that to 70 degrees, and that one should be pretty reliable. And I've also heard from some of the guys that use these, when they use these really small temperature probes, and sometimes they're trying to shove it into the same pipe as the original thermostat, and then they end up damaging the wire because there's just really not a lot of space in there. So I don't really like this way of doing things. So I think the method that I'm using should give us the best results and should work across pretty much any standard geyser. Something of concern is the son-off switch overheating in the closed box. So depending on where you live, this may or may not be a problem. Where we live, in winter, it's definitely not a problem, but as summer rolls around and temperatures increase, it may be a little bit touch and go, so I might need to extend the son-off device into a cooler area. But nevertheless, so far it has been running with 3 geysers over the past 2 months, and it's been working really great. So let's have a look at some of the graphs. So this is the temperature graph of one of our geysers, and it runs from 16 May 2024 to 17 May 2024. So it's just basically one 24-hour period. And if you remember earlier, I mentioned that the geyser is set to turn on at 12 o'clock midday. So here it was at 32 degrees C, and it turned on and then eventually reached 65 degrees C at 1:30 in the afternoon and then turned off again. And then as the day progressed, then the water temperature slowly decreases, and the first evening shower we had here at 5:42, and then the second evening shower we had here at roughly 7:45. And then after that, as the evening progressed and as we got into the next morning, you can see the water temperature slowly decreases. And then the first morning shower on this day was at 5:26, and the second morning shower was at about 7:48 in the morning. And after that, again, you can see the water temperature slowly decreases until 12 o'clock rolls around, where the geyser element turns on once again, and then it starts heating. So you'll notice here that we didn't even have to bump the temperature in the morning. It was enough for one heating cycle to get 4 showers out of it. So now we're looking at the inverters graph, and you can see this is also for the period of 16 May 2024. So basically the same 24-hour period. And the two parameters we've got displayed here is our grid power in blue and then our solar power in purple. So remember, the geyser was set to turn on at 12 o'clock midday. So if we head over here to 11:56, we can maybe get closer there, 11:58. There, our solar power, there was 2.1 kilowatts. And then straight after 12 o'clock, the geyser turned on. We can see our solar power shot up to 8.8 kilowatts at 12:03. So of course we had the geyser turning on, and there must have been 1 or 2 other items that turned on because it's only a 4 kilowatt geyser. And then as time went by, we completely used the solar power to heat the geyser. But you can see here at roughly, what is this, 12:44, there must have been a cloud that came over, and we can see that our solar production dipped a little bit, and we had to sort of supplement that with our grid power, which is in blue. But then by 12:53, maybe the cloud went away, and then our solar production was back up, and then it continued only using solar power to heat the geyser. And then if you remember back from the previous graph, the geyser turned off, or it reached 65 degrees at 1:30 in the afternoon. And you can roughly see that 1:30 in the afternoon here, where we were drawing 7.4 kilowatts, and then we had a drop off down to 4.3 kilowatts. And then the geyser turned off. Now, of course, the rest of the day, we also had other appliances that were also drawing power. But basically the point of this is to show you that we used very, very little grid power, and most of the power came from our solar production. So as we can see, by being able to control our water heating to different temperatures at different times, this is going to go a long way to optimizing the system so that our solar system can start paying for itself. Now, this is all good and well if you've got good weather. But of course, there are those bad weather days where unfortunately we do have to use power from the grid. But those are here and there, and they are to be expected. But nevertheless, this system, if you get it mostly configured, it should get you 85 to 90% of the way there, so that it's mostly optimized so that you can pay off your system as fast as possible. Now, what about the remaining 10 to 15% of optimization? And this is the technical part. Now, I'm not sure if this is really going to be worth the effort, but taking into account a solar forecast and potentially an upcoming load shedding schedule and how much inverter capacity is still available, and maybe even how much battery capacity is available, and we put all of this together and then come up with a set of rules for when it is best time to turn on or off the geyser so that we always have hot water, but at the absolute lowest cost. Now, I haven't quite got to this point yet, but I am looking into it using Home Assistant, although I think this is more applicable if you are in a completely off-grid situation where every single bit of energy counts. But nevertheless, if we can optimize it, why not try? Another thing to keep in mind is that results may vary, especially for smaller capacity geysers. So what I mean by this is that a large capacity geyser, something like a 200-liter geyser, has a much larger thermal mass or energy storage capacity. So if we have, say, 2 showers out of that 200-liter geyser, the water temperature only drops by a very small amount. If we were to compare that to having 2 showers out of a 100-liter geyser, you're going to have a much larger drop in temperature. So I guess what I'm trying to say is, depending on your specific installation and what arrangement you've got at your house, you may need to test and see which works best for your specific example. But I almost want to say that if you have a lot of solar power available, having an oversized geyser is going to be beneficial, but only if you can heat that geyser completely using solar power. Maybe 2 small geysers in series might be a better option. You know, for those bad weather days where we have to use grid power, the power that we pay for to heat our water, then we only heat one of the small geysers, so it doesn't cost that much, and then we just use the hot water sparingly. I guess you guys let us know what you think in the comments. I'm also sure some of you are saying that, hang on, this is not free power. You had to pay a large sum of money up front for the solar power installation. And yes, that is absolutely correct. So technically, in the beginning, it's not free power. But as time goes by, hopefully the cost of the installation will be equal to or less than the energy saving or the electricity bill saving that you've made if you would have been paying for that grid power. And then after that point in time, well, then the power becomes free. So if you want to see more about these DIY solar inverter battery systems, go check out this video right here. Also, as time goes by, if there is any additional information, I'll add it to the description, so make sure you go and check that out. Well, if you found the video useful, please give it a thumbs up and please share it with anybody else that you think might find benefit from this. Thank you guys very much for watching, and we'll see you next time. Cheers.